So what we've been going over last few days is being able to identify a reaction, okay, as either a synthesis, decomp, single replacement, double replacement, or combustion. Seems like we're getting that. Okay, working on being able to balance them and being able to write them out, which is mostly just being able to write the formulas and the names properly. Okay, what we're going to start today is predicting the products. We looked at that yesterday with question 7 on the quiz, okay, but we're going to look at that in more detail today. Okay, we're going to go over kind of the steps that you need to do in order to properly balance a chemical, or sorry, to properly predict and then balance a chemical reaction. Right, now you can see yesterday that predicting the products really isn't all that big a step from what we've already been doing. Okay, all of the reaction types start differently. Okay. If we can identify what kind of reaction is going on just from the reactants, and we can predict what the products will be, because all of the reactions, and we only have 5, all have specific patterns that they follow. As long as we know those patterns, prediction is easy. Okay, especially for combustion reactions where the products are always the same. What are always the products of any combustion reaction? Water and CO2. Right? I mean, that's just one you can memorize that and just write it down. Those are always going to be the products. Okay, so key points for today. Understand that the amount of atoms on the reactant side of an equation must be the same as that on the product side. We've already done balancing. This is just so that you actually have official notes on how the balancing works. So we're going to zip through those because you guys seem pretty good at that already. Okay, learn to use coefficients to balance equations, and then understand matter can't be created or destroyed. That's the law of conservation of mass, or law of conservation of matter, whichever way you've heard it phrased. Okay, that's the whole reason that we balance chemical equations. I cannot have more material after a reaction than I had before. I can also not have less material after a reaction than I have before. Okay? Early on in the science of chemistry, people didn't necessarily think that was true. And the reason being is sometimes matter would escape during the reaction. Doesn't mean that it wasn't around, it just escaped. It wasn't contained. Right? In particular, this would happen in reactions where what was formed? Gas. Okay? Gas has mass, right? We don't think it does because we don't feel it, and we're surrounded by gas all the time. Okay? But we do feel it. We just don't realize that we feel it. Okay? How do we know that gas has mass? Well, because there's atmospheric pressure. The weight of the atmosphere pushing down on us has certain biological effects on our bodies. Okay? If you've ever gone uphill or downhill a long way in a car, your ears probably popped. Okay? You've all had that experience, right? Okay, that's because the amount of weight pushing on your eardrum decreased or increased, okay, depending on whether you were going up or down, and you had to equalize the pressure that was behind the eardrum with the pressure that was in front of the eardrum. Usually you just do that by swallowing or chewing some gum or something like that. Okay. Other things that you may have noticed, if you've ever fully inflated a completely empty tire, all right, if you have a tire on a rim, okay, and there's no air in it, pick it up. Then fill it up with air and pick it up. And it will be noticeably heavier after you pump it full of air. Okay? I mean, you're going to put several kilograms worth of air into that tire when you pump it full of air. Okay? I mean, in general, tire inflation is somewhere around 30 to 35 pounds per square inch of pressure. I know that's an imperial measurement, but that's what we all use. It's kilopascals. I don't remember how many it is. Okay? But yeah, you're going to have enough air in there that in every square inch of the tire, if you would have to push, okay, with 30 pounds worth of pressure to get in. Okay, that's how hard it's pushing out. So there can be a lot of air and thus a lot of mass. But if people weren't, during their reactions, containing that gas, they would find that their products had less mass than their reactants, and they go, well, I destroyed matter somehow. Well, no, they didn't. Okay, they just didn't contain the gas, and as a result, it escaped. Sometimes when we have time, we actually do a lab where we have a sealed container, okay, where we produce a gas in a chemical reaction. Okay, the gas gets contained, then we pop the seal and allow the gas to escape and take the mass again, and we do get a noticeably different amount, okay, or different measurement on that. Okay, so mass always has to be conserved in reactions because matter cannot be created or destroyed. That's the law of conservation of mass. Okay, that's an important thing for us to know. And if we look at this reaction here, okay, we'd have two hydrogen molecules containing 4 hydrogen atoms, okay, 1 oxygen molecule containing 2 oxygen atoms, okay, and over here we have exactly the same amount of material. If we have the same amount of material, we should have the same mass before and after. Okay, so that's the balancing, or the reason we do the balancing, but like I said, we've already kind of covered that. Okay, in which one of those pictures, B, C, or D, is mass being conserved? D. Okay, over here, there aren't enough yellow atoms. Okay, there's way more yellow atoms up here in the reactants than there are down here. So the mass is not being conserved in this one. Okay, in this one, it's just obvious that there's way less matter in C than there was up here in A. Right? The thing that throws people about D is that we didn't make all these molecules. Some of these things are still floating around freely by themselves. That's okay. And in fact, in most reactions, that's what happens. Okay? Most reactions don't work perfectly like we write them out and say, look, I started out with exactly this many and I ended up with exactly this many. You usually don't have exactly the same amounts of both reactants. And so you have a little bit of one of them left over after the reaction. Okay? And you'll see this when you do your lab tomorrow. One of the pairs of things you're mixing is vinegar and baking soda. Okay? I mean, if that reaction happened completely, there wouldn't be any baking soda ever left on the bottom. Okay? We would create other compounds that would be soluble in water, and it would disappear completely. The problem is that we never get it exactly right. Right? We might look like we're pouring equal parts, but we're not. Right? And so there's always going to be something left over at the end. These individual yellow ones are the ones that were just left over. There wasn't enough red stuff there to react with all of them. Okay? That's still mass being conserved. I still have the same number of atoms on both sides. We never show that really in at least a grade 10 level reaction, but you might by the time you get to Chem 30 have to say, I had an excess of this, and so it was this many grams at the end. Okay. Now, balancing chemical equations, like I said, this is just so you have some formal notes on it. Okay, you write the chemical formula for each reactant and product. Well, you don't have to include the state of matter. That still says that in your notes. Cross it off because you guys don't have to do the state of matter. Okay, try balancing the atom or ion present in the greatest number. Okay, we've said that for all reactions except combustion, which has its own balancing rules. Okay, use coefficients, that's numbers in front of the element or compound, to get equal numbers of atoms on both sides. Essentially what that's saying is don't change little numbers. Okay, if you're told, oh, that's really hard to see. Okay, if you're told you have this stuff, you can't just go, oh, well, I need 2 chlorines. I'll just do that. Okay, can you balance a reaction by doing that? No, because that's not sodium chloride anymore. That compound doesn't exist. Okay, I can't change what I have, but I can put a coefficient in front of it and change how much of it I have. That's all you can do to balance a reaction is change how much, not change what. Okay? And then step 3, repeat step 2 to balance each of the remaining atoms and ions, and we've seen how you kind of go back and forth in a reaction in order to get it to work. Okay? Step 4, double check. That's the step people forget. Okay? They get to the last thing like, sweet, I got all the blanks filled in, and they don't double check to see if their last thing might have thrown something else off, because it sometimes does. Okay, so it's always a good idea when you think you have it balanced to double check, make sure nothing got thrown off, and something that's not on here you might want to add, step 5. If possible, reduce coefficients to the lowest terms. Okay, once in a while, we just pick a number that's too big, or we had that odd even problem we talked about, and we doubled something, and then when we get done, it ends up that we didn't have to. Okay, it doesn't happen very often, but it happens once in a while. So if I end up with a reaction that's balanced with 2, 4, 2, 2, should I leave it that way? No, I can reduce all of those. All of those can be divided by 2, and I would balance that then as 1, 2, 1, 1. Okay? I should always reduce down to the lowest terms. Again, it is not something that happens very often, okay? But it is still something you need to check for, because if you leave it like this, it's wrong. Okay? Always has to be balanced in the lowest terms. While it may be balanced, it isn't balanced in the lowest terms. Sometimes you don't always see it. Yeah. Most of the time you would. That's what I'm saying. This doesn't happen often, but it happens often enough that sometimes it costs people marks. So just it's not something to be watchful for. It especially happens, people sometimes over-apply the rule of 2 on combustion reactions. They just put a 2 in front of all of them. And if you do that on an odd number of carbons, you'll find that you'll be able to reduce it down, everything divided by 2. Okay. All right, questions on those? You guys have been doing that already for several days, so it's just so you had some formal notes on it. Okay, and obviously we've done this reaction a whole bunch of times, okay, as an example, but this is how you would get a question like this. You would get it in words, like it's shown up here at the top. Copper wire is immersed in a solution of silver nitrate. A single replacement reaction occurs, and that's it. Now you got to predict the products. Okay, so in a reaction like that, instead of looking at all the steps here, we're just going to set it up. Okay, so a piece of copper wire, is immersed in a solution of silver nitrate. Okay, so that's a metal. This is an ionic compound. This is a -1 and this is a +1, so it's okay on the drop and swap. Okay, I have an element reacting with an ionic compound. Okay, the question already said the single replacement reaction occurs. That's not something I would tell you. Okay, I would just say a piece of wire, copper wire, is immersed in silver nitrate. Predict the products. Right? So at this point now, my first step is identify the, well, first step is write it out. Then identify the reaction type. Okay? This is a single replacement reaction because I have an element reacting with an ionic compound. What kind of element do I have? It's a metal. Okay? That's important for me to recognize because now I know what in this ionic compound needs to get replaced. So what is copper going to replace? Silver. It's got to replace the thing it's like. All right, so I'm going to end up with copper nitrate and silver. Okay, I have a problem with copper nitrate. What is it? It might. It might need brackets. And I haven't dropped and swapped it. And the reason I haven't dropped and swapped it is because, right, this question started out with copper as an element where it does not have a charge. So now I'm on this side and I'm stuck. I don't know which copper this is. Is it 1 or 2? What do I do? But I can't. I predicted this product. That's why I'm stuck. I know copper has to go with nitrate, but I don't know if this is copper 1 or 2, so I don't know how to swap and drop it. Okay? I can't use the nitrate here to figure it out because it wasn't with copper over here. Right? I don't know whether I should have CuNO3 or CuNO3 2. Either one of them is a possibility here. So, here's the rule. Take out your periodic table. All multivalent metals have their charges listed from left to right in order of their, I want to say popularity, but that's not the word. The most common charge is the first one listed. Let's say it that way. Okay? So what's copper's most common charge? 2. Okay? In reality, copper is 2 almost all the time. Okay? You almost never end up with copper 1. It's a far less common charge. Okay? So if you run into this situation, and you will occasionally, you go with the most common charge. There was no way for me to figure out what copper was because it wasn't with anything over here. So over here, I go with, all right, it's 2 plus because 2 plus is more common than 1 plus. So I'm going to go 2 plus, 1 minus, drop and swap, and have this. Okay, I've predicted the products of my reaction. Now what do? Now I got to balance. Okay, only thing that's out of balance right now is nitrate. There's how many of them? 2. Now what do I have to do? I have to make sure there's 2 silvers over here. And now we're good. Okay, does that make sense? Single replacement reactions have the most things that can go wrong in them. Okay, in that they can sometimes produce special elements. Okay, if this was a non-metal, so if I had another single replacement reaction where I had, let's say, chlorine reacting with sodium oxide. Okay, it's another single replacement reaction. Okay, except that this time the element is a non-metal. Who's it going to switch with? With the non-metal. So sodium's going to end up with chlorine, and oxygen's going to end up by itself. Right? So I'll have sodium chloride, and that's a 1 and 1, so that's good. And I'm going to have oxygen, except that oxygen is a special one. Okay? So lots of single replacement reactions have the potential to produce our molecular elements that we have to remember have 2s or 4s or 8s or whatever they happen to be. Okay? So we have that. We have problems that could occur with multivalent metals because we're dealing with ionic compounds. Just single replacement ones have the most things you have to think about and remember. Okay? Synthesis reactions are easy. It's 2 elements, they go together, you just put them together and make a compound. Okay? They're fairly hard to screw up unless I do this. This is a trick that I do all the time. You don't have to. I'm kind of doing it out of habit. If it was a fill in the blank question, you have to. Yeah? Otherwise, I don't know whether you did it or didn't know how to do it. Yeah. Okay. So let's say I'm looking at this synthesis reaction and I write it this way. Okay, so I have a synthesis reaction. I got to make a compound out of those. What should it be? Potassium chloride. How would I write that? KCl. You would be surprised how many people will do this. Because I put the non-metal first in the reactants, and they'll write it wrong, even though they know full well that an ionic compound is never written this way. Okay? I just told you one of my tricks. My bag of tricks is not very full. Okay. Exactly. Yeah. Okay. So, but I mean, the steps are going to be similar for all reactions. It's going to be identify the type, make the products, swap and drop ionics, look for specials, balance the reaction. Okay. Basically, that's what you have to do with all of them. Okay. The one thing I won't do is have you have a synthesis reaction that would make a molecular compound. Right? Why would I not give you one like this? Well, it's not so much that you wouldn't know which one. I mean, you kind of wouldn't know which one to go first, but how do you know how many of each there's going to be over there? Right? You can't swap and drop a molecular compound. Nitrogen and oxygen can go together like this. They can go together like this. They can go together any number of ways. Okay? There's no way for you to know which way they would be going together. So I would never give you a synthesis reaction predicting a molecular compound. Okay? Because you can't predict a molecular compound, essentially, because there's no way to know how those two things are going to bond. They might bond in like 3 or 4 different ways, and you could have 4 different products. That's not fitting the mold, okay, for what we're doing. So if I give you a synthesis reaction, it's most likely going to produce an ionic compound that you can drop and swap. Okay. I want you guys to try those 4. Okay, I want you to predict the products and balance it. That's all you have to do. You don't have to write it out in words or anything like that. Just predict the products and balance. Let's see how we do. So like we said, the first step in predicting the products of a reaction is obviously to write the reactants. That's already done for you. Okay. Second thing is I got to identify the type of reaction that's occurring so I know what pattern to follow. In number 1, I've got 2 elements that are reacting. So what kind of reaction is that? Synthesis. Okay, so in a synthesis reaction, the 2 elements combine to form a single compound. So calcium with oxygen. Now I've got to do what with this compound? yeah, drop and swap it, right? This is a -2, this is a +2, so it's already good that way. Okay, now I've got to balance the whole reaction as my final step. There's 2 oxygens over here, so I need to put a 2 there to balance the oxygens, and then a 2 here to balance the calcium. Okay, does that make sense to everybody? All right. Number 2 has only one reactant. There's only one reaction that starts that way, and it's decomposition. So it's got to break down into its component elements. So that means magnesium and sulfur. Obviously, there's no dropping and swapping to do here, but what do I need to be checking? Right, I got to look for special elements. Magnesium's a metal. There's no special metals other than hydrogen. Okay, and sulfur is very special. Comes as an 8. Right, so you always got to look for those in decomp reactions as well as single replacement reactions. They're going to produce a lot of special elements. Always be watching for those. Now I've got to balance the reaction. Start with the biggest number, 8. Okay, so I go over here and I put an 8 in front of magnesium sulfide, and then I have to put an 8 in front of magnesium to make it work. Okay, how many people have done number 3? Okay, let's have a look at that one too. What kind of reaction is that? It's a combustion reaction. So the products are always CO2 and water. Okay, so that's an easy one to predict. You just got to memorize that. It doesn't matter how many carbons and hydrogens there are, it's always carbon dioxide and water. Okay, do I need to apply the rule of 2 on this one? No, got an odd number of carbons. So I can just start with 3 carbons over there, 8 hydrogens over there, and now I can look at how many oxygens I have. 3 times 2 is 6, plus 4 is 10, 5 times 2 is 10. Okay, how many people have done number 4? Okay, I'll give you another minute on number 4. Okay, let's look at number 4 here. So I have hydrogen chloride and sodium hydroxide, both ionic compounds. What kind of reaction am I looking at? Double replacement. Okay, in a double replacement reaction, I'm going to get 2 ionic compounds on the other side, but they got to be different than these. The easiest way to do that is to do what? Swap the metals, right? So basically just do this. Okay, so in other words, we're going to have sodium with chlorine, okay, and hydrogen with hydroxide, in other words, water. Does it matter which order these go in? It doesn't. Water could come first and sodium chloride could come second. As long as you got metal, non-metal, metal, non-metal, you're good. It doesn't matter which way or which order they go in. Okay? All right. Now I got to check drops and swaps. +1, -1, +1, -1. So those are good the way they are. Do I need to do any balancing? No, there's no small numbers, so everything's a 1. Okay? Everybody all right with that? Hey, is that making some sense? It really isn't a lot different than what you've been doing. Okay, predicting the products. I mean, you can thank Dalton for this, right? And I think we talked about this before, but Dalton's atomic theory says that in a chemical reaction, atoms can be separated, joined, or rearranged. Right? That makes prediction easy. You know you can only have the stuff you started with. You can rearrange it, you can separate it, you can join it, but you can only have what you started with. Okay? You're not magically turning something into something else. Right? So this is kind of going along that point of Dalton's atomic theory, which incidentally will be part of your hypothesis for the lab you're doing tomorrow. Okay? We are going to do the pre-lab today in about the last 20 minutes of class. All right. Okay, the flow chart can help you with each one. So, okay, write out the reactants. That's our first step. Okay, swap and drop any ionic compounds and check for special molecular elements right at the beginning. If you're given the reaction or the reactants, sorry, in words, okay, you would have to do that. All right. If your reactants are 2 elements, for example, sodium and chlorine, that would be a synthesis reaction. So we're over here, okay? What do you do in a synthesis reaction? You put the elements together into a compound, okay, like sodium chloride, and then balance. Okay? If your reactant is only 1 compound, okay, then it's a decomposition reaction. Split the compound, write the elements separately, check for special elements, and balance. Okay? If you've got CnHY plus O2, okay, then you have a combustion reaction, and the products are always carbon dioxide and water. We have our special balancing rules here, balance in alphabetical order, CHO. There's an even number of carbons, put a 2 coefficient at the beginning, okay, so you can balance. If your reactants are an element and 1 ionic compound, so the example here is Ca and CuSO4, you're looking at a single replacement reaction. Okay, look at the lone element, identify it as metal or nonmetal. Then use it to replace its counterpart in the ionic compound. Switch a lone metal for the metal in the compound, lone nonmetal with the nonmetal. Okay, swap and drop your new ionic compounds, okay, and check the new lone element to see if it is a special element. So you can see, as I told you, there's more things to remember and think about and check in a single replacement reaction than there are in any of the others, right? If it's two ionic compounds, like NaCl and HBr, it's double replacement. Swap the metals, swap and drop your new ionic compounds, balance the reaction. So if you want to, you can copy down that flow chart, but like I say, it's not something that you necessarily have to have. All right, so I'll give you a few minutes to try these, and then we'll go through them together. All right, let's have a look at number 5 here. Okay, so I've got two elements reacting with each other. We've got what kind of reaction? A synthesis reaction, right? So we need to combine them into a compound. Okay, and beryllium has a charge of +2. Iodine has a charge of -1. This is an ionic compound because it's metal and nonmetal. So we're looking at BeI2, which means that we don't have to do any balancing because everything is already balanced. Okay, questions on 5? All right, let's have a look at number 6. All right, I've got potassium, and then it's reacting with iron 2 oxide. What kind of reaction am I looking at there? Single replacement. All right, so in a single replacement reaction, what I'm supposed to do is look at the lone element. The lone element is a metal. That means it's going to swap out for the metal in the ionic compound. That means iron is going to be by itself, and potassium is going to end up with oxygen. Okay, iron's a metal. It's not a special element, so it doesn't require any small numbers, but this is an ionic compound. -2 and +1 means that this needs to be K2O. Okay, and the last thing I have to do is balance. If I put a 2 here, that should make everything work. Questions on those two? How many people have done number 7? Okay, let's have a look at 7 as well. All right, so I've got copper 2 sulfate reacting with magnesium chloride, 2 ionic compounds. So this is a double replacement reaction. So all I'm going to do is swap the metals. Okay, so that means that copper's new partner is going to be chlorine, and magnesium's new partner is going to be sulfate. Now, magnesium sulfate is okay. That's a -2 and a +2, so it's swapped and dropped correctly and requires no brackets. What do I do with the copper and the chlorine? City? Right, over here in the reactants, this is copper 2. Right? If there's a way for me to figure out what the charge is, I should do that. Okay? I showed you an example earlier where there was no way for me to figure out what charge copper had, so I had to go with its most common charge. In this case, I can figure out, okay, that copper must have been a +2. Okay? So that's what copper is over here. It's not going to change. This is a +2, this is a -1, so I've got CuCl2. Everybody follow me there? Looks like everything is balanced, so I don't have to add any other numbers. Questions on number 7? How many people have done number 8? Okay. I'll give you a couple more minutes and I'll go through 8, 9, and 10. Okay, number 8. I've got ethane. Okay, sorry, butane. Butane, that's what that stuff is. Okay, it's the stuff that's used in lighters. Okay, is reacting with oxygen. What kind of reaction is it? Combustion reaction. I've got carbon, hydrogen, and oxygen as my reactant. It's got to be combustion, which means the products are given. They're carbon dioxide and water. Okay, I don't have to do anything else in terms of dropping and swapping or looking for any of that. Okay, now I've got a balance. Do I need the rule of 2? Yes, I do. All right, so I've got 8 carbons. Now I've got 8 carbons over here. I've got 20 hydrogens. Now I've got 20 hydrogens over here. That gives me 10 oxygens in the water and another 16 in the carbon dioxide for a total of 26. 13 times 2 is 26. Everybody all right with number 8? How many people have done 9? Okay, so let's have a look at that one too. All right, so I have rubidium phosphide. all by itself. It's the only reactant. So this is a decomposition reaction. All right, so that means break it up into its two parts. Okay, rubidium's a metal. Okay, so it's not special. Phosphorus is. So it's P4. Now I can start my balancing. Okay, I should balance the largest number first. So I'm going to go with phosphorus over here. I need to put a 4 in front of this to get my proper number of phosphorus, which gives me 12 rubidium. Okay, anytime I have big numbers like that, it's always a good idea to check for that reducing thing. Okay, but because phosphorus over here is a 1, that's the smallest terms it can be. Okay, how many people are done 10? Okay, let's have a look at it. What kind of reaction is it? Double replacement, all ionic compounds. So we're going to swap the metals. So Pb is going to end up with phosphate. Sorry, shouldn't put the brackets in until I'm sure I want them. Okay, and cobalt is going to end up with chlorine. Okay, do I have any multivalent metals in there? Both of them are. Okay, so over here, chlorine's a -1. Okay, that means that this lead had to be the lead of the 4+ variety. Okay, and over here, phosphate's a -3, which gave me a total of 6 negative charges. Okay, so I have 6 positives, 3 of these. That means cobalt was a 2+. So I've got 4+ lead, and I've got 2+ cobalt. So now I can do my dropping and swapping. Okay, this is a +2, this is a -1, so I've got COCl2. This is a -3, and this is a +4. So I'm going to have Pb3PO4 4 when I drop and swap. I see a few jaws dropping. Where did I lose you? Okay, all right. It's not that the jaws dropped, it's just that you're too tired to hold them up. Okay, don't snore. Yeah. Okay. Now I've got to balance this reaction. Start with the thing present in the largest number. That's probably phosphate. There's 4 of them over there. So I would need to put a 2 here in order to give me 4 phosphates. When I do that, it's going to give me 6 cobalts. So I got to go back over here and make 6 cobalts. Everybody with me so far? Okay, when I do that, it gives me 12 chlorines. So I got to go back over here and make sure I have 12 chlorines. That gives me 3 lead. Good sign. There's 3 lead over here. Okay, looks like I'm done. Okay, questions on how that works? Those will be your biggest mark getters on your unit exam. Okay, you're also going to have an assignment that we're going to start next week that's all reactions. Okay, it's got 30 reactions on it. Right, what you have to do for some of them is just balance and write them out. Other ones you got to write them out in formula form and balance them and tell me the type. Okay, and in the last 10, you have to predict the products. Okay, so it's kind of your last assessment of reaction before we start the mole equation. Okay, and move into the last part of the chemistry unit. So probably by the end of this week, I will let you know when your unit exam is going to be, as I think we're getting around the 2 weeks away mark here. Okay. Any other questions on those 10? Okay, how many people are done the worksheets that I gave you the other day? Okay, a few of you are getting there. Good. All right. So what I want you guys to do right now, don't worry about these balancing questions up here. Okay, they're beyond anything I would ever ask you. They're just there. If you're starting to feel like you can do anything, these will humble you. Okay, so if you're starting to feel cocky about how well you can balance equations, these will be a humbling experience. All right. What I'd like you guys to do here is these first 8. Okay, so just write them down in your notes there and do them. Okay, make sure you write down the actual question. Don't just write down your answers. Write down the questions. Okay, and then predict the products. And I'll go through those right before we start our stuff on the pre-lab here.